So we're now in chapter 3, which is dealing with two-dimensional motion. Now the key thing is that a lot of these involve something being thrown at an angle, and you have one direction where you have no acceleration, which is typically the horizontal direction, and you have the vertical direction, which is constant acceleration, which is acceleration due to gravity. And you look at each one of those separately, and you look at velocities, accelerations, and displacements separately. The time, though, has to be the same between the two directions. It's kind of the connector. So we're going to start with 23. And so what we have is we have a student who is standing at the edge of a cliff. So here's my cliff. And he throws a stone horizontally over the edge with a speed of 18 miles per hour. So we're going to show a little arrow here to show the vector of the velocity. It's horizontal, 18, actually meters per second. I'll go over miles per hour. 18.0 meters per second. And the vertical velocity is 0. The cliff is 50 meters above a flat horizontal beach. So the height here is 50 meters. And then we have a beach right here at the bottom. That's the horizontal beach. Okay. And so what's going to happen is going to throw this, and it's going to go out horizontally, and then it's going to start going like this, see parabola, and down until it hits the beach. Okay, so what are the coordinates of the initial point position of the stone? Well, that depends upon how you define the initial position. So well, let's look at the graph, see if they've got where they're showing. Okay, I'm trying to figure out exactly where the origin is. This is the bottom of the cliff. So that's where we're going to start right here. And the coordinates we're going to call 0 meters x and 0 meters y. So the coordinates here of the stone, the coordinates are going to be 0 meters x and plus 50 meters y. And that's because we would define positive y in this direction and positive x in this direction. So you, like with one-dimensional motion, you have to define the coordinate system and also which way is positive. So since this point here is 50 units above in the positive y direction, plus 50 meters. Okay, second question, what are the components of the initial velocity? Well, the components of the initial velocity, so let's just write this is B. Sorry about that. So this is part B. This is part A right here, coordinates. So the initial velocity just has a horizontal component. So what we can say is V0, because it's the initial component, sub x, V0 sub x is equal to positive 18 meters per second. And because it's horizontal, V0y is equal to 0 meters per second. Okay, third question. Write the equations for the x and y components of the velocity of the stone with time. Okay, I'm going to add another page here. So this is part C. So in the x direction, what do we have? Well, in the x direction, we have, this is constant velocity, because there's no acceleration acting in the horizontal direction. So that we only have one equation, which says delta x, so the change in the x position, is equal to the velocity in the x direction, which is the initial velocity in the x direction, times the time. So that's the equations for the x component. For the y component, we have both, well, we have constant acceleration because we have deceleration due to gravity. And because of that, we have 4 equations. But it says Write the equations for the x and y components of velocity. Well, actually, this is v0x equals 18 meters per second. So that's the equation for the velocity. And as far as the y direction is concerned, we have v sub y, which is the y velocity, is equal to the initial y velocity plus the acceleration in the y direction times time. So that's the equation for the y velocity as a function of time. So this is constant, and this turns out to be linear with time. Write the equations for position of the stone with time using coordinates in figure 3.23. So we're going to use this right here, and so delta x is equal to x minus x0, and that's equal to v0x times t. But x0, that's this x coordinate is 0 meters. So we can say that x as a function of time, because that's 0, you just have x, is just equal to v0, which is 18 meters per second, times the time. So the position varies linearly with time. So that's the x direction. In the y direction, what we have is we have y, delta y is equal to v0y times t plus 1/2 a y t squared. And delta y is equal to y minus y0. And y0 is equal to 50 meters. v0y is equal to 0 meters per second. That's from this part right there. We know that the acceleration in the y direction is negative 9.8 meters per second. And it's negative because the acceleration is downward and positive y is upward. So if we plug those in, delta y is y minus y0, and that's equal to v0, which is 0, times time, plus 1/2 times negative 9.8. So it's 1/2 times negative 9.8 meters per second squared times the time. This drops out, and so we get the final number. Y is equal to, if we add 50 to both sides, we have y is equal to 50 meters minus half of 9.8 is 4.9 meters per second squared times the time squared. I forgot the squared here. So that is the equation for the position of the stone, of the x position and the y position. Y of t right here. Okay, how long after being released does the stone strike the beach? Well, below the cliff. Well, the thing that's governing the time is that there's ground in the y direction. So for this is part D, part E, we're going to use the y direction only to figure out the time. Because there's nothing stopping it in the x direction, there's only something stopping it in the y direction. So what we'll do is we'll use this, this equation right here, and when the object hits the ground, it is at an elevation or y direction of 0. So what we do is we say 0 meters is equal to 50 meters minus 4.9 meters per second squared times time squared. So now all I have to do is solve for time. So what we'll get is t squared is equal to, subtract 50 from both sides, we get negative 50 meters divided by negative 4.9 meters per second squared, because the 0 here is just 0. And when we do that, we'll get negative 50, sorry again, negative 50 divided by negative 4.9. Just can't seem to do this. Just 50 divided by 4.9. I get that 10.2 meters squared per second squared. Take the square root, and you take the positive version because we don't have negative times, so we take the square root of 10.2. 10.2 to the 0.5 power is 3.2 seconds. Let's think about significant figures here. As far as I can see, we've got 3 significant figures, 50.0, 18.0, all the other ones. We have as many significant figures as we want, so we're going to have 3.19 seconds. So that's the time it takes to hit the ground. And now I think the final question is, with what speed and angle of impact does the stone land? Okay, so we just have to calculate the velocities after 5 seconds. So, well, we know the x component of velocity. The x component is just equal to v0x, which was 18 meters per second. V sub y is equal to v0y plus a sub y t. So now we have t, so we can calculate this. So our y component of velocity is our initial y component of velocity, which is 0, plus a sub y, which is negative 9.8 meters per second squared, times the time, which is 3.19 seconds. So we get negative 9.8 times 3.19. And so v sub y is negative 31.3 meters per second. So those are the components of the velocity. To find the actual velocity, what we do is we take those two components, v sub x, which is positive, and v sub y, which is negative, and we use the vector sum of those two, which is this. So this is v sub x, 18. This is v sub y, which is negative 31.3. And we get this because it's a right triangle. To find v, our final velocity, it's equal to the square root of v sub x squared plus v sub y squared. And that gives us the magnitude. So take the square root of 18 squared plus negative 31.3 squared decimeters per second. So let's square those two and add them together. I get 1,300. I get the square root of 1,300. And square root of 1,300 is 36.1. 36.1, 31.6. Meters per second. So that's the velocity. And the angle of impact we get just using geometry. So we've got a right triangle here. This is the angle. Depends whether you do it with respect to the horizontal or the vertical. So we'll do it with respect to the horizontal. And so then we just use geometry here. And so we're going to use, this is the opposite, and this is the adjacent, so we use the tangent. So you know that the tangent of theta is the opposite divided by the adjacent, which is 18 meters per second. So 31.3 divided by 18 is 1.73. And if we take the inverse tangent of that, find it, 60 degrees. So theta is equal to the inverse tangent of 1.74, actually negative 1.74. So theta is actually negative 60 degrees. It's negative because it's pointing downward into the fourth quadrant. So that is the answer. And I'm going to pause for just a second and make sure those answers are correct. Okay, so I've checked the answer and everything's correct. Sounds good. Okay, 23 was pretty involved, and it is a blue problem, which means it's a harder problem. It's kind of surprising it's the first problem almost in the section, but okay, the next one we have assigned is problem number 30. So it says we have an artillery shell is fired with an initial velocity of 300 meters per second, 55 degrees above the horizon, horizontal. To clear an avalanche, it explodes on a mountainside 42 seconds after being fired. What are the x and y coordinates of the shell where it explodes relative to the firing point? Okay, so let's draw something here. It looks like a cannon. So there's your cannon. And we're going to incline this at a certain angle, which is 55 degrees. Okay. And we're assuming that this is the 0 point right here. So we'll define this as 0, and let's go ahead and put the axes in there. So this is your y, that's positive y, this is positive x. The actual velocity comes out of here, 55 degrees, so this angle is 55 degrees. So theta is 55. The velocity, and that's the total velocity, not the components, is 300 meters per second. And that flies through the air. Actually, let's start here. Go like that. After a certain amount of time, it's going to go explodes, makes noise, causes the avalanche to happen. The question is, what is the coordinates? What are the coordinates here? X and Y when it explodes. Okay, so just like in the previous problem, we have in the x direction, we just have constant velocity. And the constant velocity is the initial velocity in the x direction. In the y direction, we have constant acceleration. And the acceleration is equal to negative 9.8 meters per second squared. We know here that x0 is equal to 0. And here we know that y0, our initial y displacement, is also 0. We also have an initial y velocity. And then we also, here we have time, and here we have time. Time being 42 seconds. So with all that information, with this, we have the constant velocity expression, which gives us delta x. And since x0 is 0, delta x is equal to x. So we can get it from there. And this one, we have the 4 equations that we can choose whichever one is appropriate. So we're going to calculate the delta x first. Delta x is equal to x final displacement minus the initial displacement. And that's equal to v0x times time. Well, v0, let's go over here and just draw a vector diagram. So you have, here's v. v0x is the x direction. v0y is in the y direction. This is the right angle. So this is equal to 300 meters per second. This is equal to 55 degrees. And so from geometry, we know that this is called V0y, this is called V0x. This is the adjacent side, this is the hypotenuse. So we know that the cosine of 55 degrees is equal to V0x divided by 300 meters per second. Cosine is a dimensionless number, so since this is meters per second, this is meters per second, the answer is going to be meters per second. So you get V0x is equal to 300 meters per second. We'll assume it's three significant figures times the cosine of 55 degrees. I don't know if they say 55.0. Yes, they do. So that's also three significant figures. So we get V0x is, make sure I'm in degrees. Yes, I am on my calculator. So we have 300 times the cosine of 55 degrees, which should be a little bit more than a half, which is 172 meters per second. So now we can just plug in here. So we know x is equal to x0 plus v0x times t. x0 is 0, so it's just going to be equal to v0x, which is 172 meters per second, times the time, which is 42 seconds, 42.0 seconds. We have three significant figures. So 172 times 42, we get 7,230 meters. So that's our x displacement. Now to find the y displacement, we have, well, what are we given? We're given v0y, acceleration, and the time. Okay, so this, we'll use this equation which says delta y, which is y minus y0, is equal to v0y times t plus 1/2 a sub y t squared. So when we're trying to solve for t, we don't typically try to go another direction, but when we're given time, we just plug directly into this equation. It's just the easiest way to get there. So remember, y0 is 0 meters. So we could let that drop out. v0y, going back to our triangle, this is the opposite side. So we're going to use the sine. So this is going to be equal to v0 times the sine of 55 degrees. Okay, so v0y is 300 meters per second, three significant figures. Sine of 55.0 degrees. I should put that extra decimal in there. So we take sine of 55 times 300, and I get 245. V0y is 246 meters per second. Okay, now we plug into here because we have everything. So we'll say y, this goes to 0, so it's just v0y, which is 246 meters per second, times the time, which is 42 seconds. And then we add 1/2 times negative 9.8 meters per second squared times the time, which is 42.0 seconds squared. So y equals, notice the units, meters per second times seconds becomes meters. Meters per second squared times seconds squared becomes meters. So we have 242 times 42, 10,164, well, 10,100, 10,200. And then we have minus 0.5 times negative 9.8 times 42 squared is negative 8,640. And because we have three significant figures, this is three significant figures, We have three significant figures. Here's those three significant figures. When we subtract it, we can go to this decimal point. We can't go there because that's not significant. So really, we take 10,200 minus 8640, and we get 15,600, which actually, I guess you'd have to round off to 1,600. Okay, so let me check the answers. Let me pause for a second. Okay, just noticed I wrote this number wrong right here. 246, not 242, so I don't know why I did that. So let's fix that. 246. 246 times 42 minus 0.5 times 9.8 times 42 squared, 1690. Which I guess could round up to 1,700. So this should be, this changes. 246 times 42. So we got 10,300. And we subtract off 8,640. And we get 1,692, so I'm going to round it up to 1,700 as far as that's concerned. And I think the actual solution manual says 1,690, but I'm not exactly sure if that's right. I think they're carrying one too many significant figures because of that. Anyway, close enough there. Okay, another blue problem. So let's just read it. This is page 78. A car is parked on a cliff overlooking the ocean on an incline that makes an angle of 24 degrees below the horizontal. The negligent driver leaves the car in neutral and the emergency brakes are defective. The car rolls from rest down the incline with a constant acceleration of 4 meters per second squared for a distance of 50 meters to the edge of the cliff, which is 30 meters above the ocean. Find the car's position relative to the base of the cliff when the car lands in the ocean and the length of time the car is in the air. So let's draw a picture. So what happens is, you can imagine the car's at the top of an incline, which is about 24 degrees, rolls down the incline and hits this cliff and then starts free falling. This angle is below the horizontal. This angle here is 24 degrees. Okay, blah, blah, let's see. And really there's two parts to this problem. The first part is where you have an acceleration and we'd actually do it along this direction. So it's just going to be one-dimensional problem for the first part. Acceleration, one dimension, with an acceleration equal to positive, because it's the positive direction we're moving, that we're defining in terms of the first part of the problem, of 4 meters per second. So it's going to speed up. Starts at rest, so V0 equals 0 meters per second. So we need one more piece of information, and it says for a distance of 50 meters. So delta, we'll call it delta S for this distance along the surface. So delta S is 50 meters. So with that, we can calculate the velocity as it leaves the cliff, and that'll be the initial conditions for the second part of the problem. So let's do the first part first. So let's see, what do we know? We know acceleration is, which is what we can see right over there. So what we're trying to figure out is what is V. We don't really need to, and I ask at the time. it just asks for the time, length of the time in the air. It doesn't ask how long it takes to go from here down to there as far as the car is concerned. So that's the question, given the stuff below here. And in terms of which one do we use, I think, so let's write them down again. So we have that delta S is equal to V plus V0 over 2 times time. We have V is equal to V0 plus AT. Delta S is equal to V0 T plus 1/2 AT squared, and that V squared is equal to V0 squared plus 2A delta S. Well, we're trying to find its final velocity. So here's final velocity, here's final velocity, and here's final. So it could be one of these three. This requires time, this requires time. So we don't have anything about time yet. So it looks like this one makes the most sense, which is the right answer. So we'll just plug it in. So we'll say the speed or the velocity of the car after it rolls down the hill is V0, which is 0, squared, plus 2 times 4.00 meters per second squared times delta S, which is 50.0 meters. And we have three significant figures. The 2, of course, has an infinite number of significant figures. 2 times 4 times 50. 400 meters squared per second squared. So that's what V squared is. And we take the square root, and you take the square root of 400, which is 20. So we are going 20 meters per second, plus 20 meters per second. So now we redo the problem. We start all over again with a new problem. Well, I guess you could say that, but here's our cliff. We have the car leaving the cliff at 24 degrees. So if we draw a horizontal line here, so this is horizontal. This angle is 24 degrees. The velocity is 20 meters per second. And then we must know something about the cliff. Cliff's height is 30 meters. So that's 30 meters. And now we're going to redefine the coordinate system for the second half of the problem. So let's start that right here at the base of the cliff. So this is Y and this is X. X, Y. From this geometry, we can find V0Y, V0X. We have the height, and what else do we need to know? Acceleration, there we go. So the acceleration is the acceleration in the y direction, which is negative 9.8 meters per second squared. The acceleration in the x direction is 0, which means, therefore, v sub x is equal to v0 sub x. It's a constant velocity situation. And what are they asking for here? The car's position relative to the base of the cliff when the car lands. Okay, well, we know it's going to be 30 meters down. The question is how far does it go out? So what we're going to do is we're going to use the y direction to find the time that it takes to fall. And then once we have the time, we can use the x direction to find the distance. And that'll give us the distance from the x direction. So that's the plan. So, and the y direction, so we're going to use the y direction first. And what do we know in the y direction? We know the acceleration. V0y is going to be equal to v sub y times, well, what is it? Is it the sine or the cosine? Well, it's the opposite side, so it's going to be the sine times the sine of 24 degrees. So let's go ahead and calculate it. V0y is 20 meters per second times the sine of 24 degrees. And it's actually going to be negative because it's going to be going down. So we have 20 times the sine of 24 degrees, which is negative 4 point. Now let's be careful with some significant figures here. So we have 20.0, 20.0, and it's 24.0. So we're gonna keep 3 significant figures. So we're gonna use 4.47. 4.47 meters per second with a negative sign because it's going down. Okay, so we know the acceleration, we know that. And we know delta y. Delta y is going to be negative 30 meters. It's negative because it's going down. We're going down. Positive y is up. We're going down, so it's going to be negative. And the equation we use is v squared is equal to, well, vy squared. No, we're not going to use that one. So what do we know? We know the acceleration, we know the initial velocity, and we know the displacement. So actually, we're going to calculate the velocity, and then we'll calculate the time from that, because if we calculate the time, we're going to have to solve the quadratic equation. We'd like to not do that, so let's go ahead and do it. V sub y squared is equal to v0 y squared plus 2a sub y delta y. So we get vy squared is equal to v0 y squared, which is negative 4.47 meters per second. 1d squared plus 2 times the acceleration, which is negative 9.8 meters per second squared, times delta y, which is negative 30 meters. So we get v sub y squared is equal to 4.47 squared, and I didn't include the negative because that just cancels out. And then we have 2 times 9.8 times 30. And again, I didn't put the negative signs in there because those cancel out. And so we get 608 meters squared per second squared. We take the square root, which means I raise it to 0.5 power, and I get 24.6 meters per second, plus or minus. Because we take the square root, we're going to use negative because we know it's going down. Okay, now with that velocity, we can go ahead and calculate the time from this equation, the second equation, which is v sub y is equal to v0 sub y plus a sub yt. So we can solve for the time. V sub y minus v0 sub y over a sub y. So t is equal to v sub y, which is negative 24.6 meters per second, minus v0y, which is a negative 4 point something. Where did I get that? Oh, it's right over here. Oh, here it is, negative 4.47. Negative 4.47 meters per second divided by the acceleration, which is negative 9.8 meters per second squared. So this is going to be a number, so you get negative 24.6 plus 4.47, which is negative 20.1. We divide by negative 9.8, and we get 2.05 seconds. So that's the time it takes for us to get down a cliff. I'm going to pause for just a second, so if I made a mistake, I'll correct it before we go any further. Okay, I apparently have made a math error here, so let's go through and fix this. This is actually negative 8.13. So if I go and put that in there, and I correct that, and so with that, I get 8.13 squared plus 2 times 9.8 times 30. I take the square root of that, and I get 25.6, 24.6, 25.6, 25.6. This is equal to 654. So this becomes 25.6, 6 minus that. 2.16. Let me just check, see if that's right answer. Oh, still had something wrong here. Oh, yeah, I got to change this here. So this was 8.13. Should be 1.87. So we have negative 25.6 plus 8.15 divided by negative 9.8, 1.78. Okay, that's it. 1.78 seconds. Okay, so once we had the time, so that was the first part. Find the cars. Okay. Well, we've done the time first, and it just turns out that's the easiest thing to do. So once we have the time, and yeah, okay, we have another page here. So as far as the position relative to the edge of the cliff, we go to the x part of the equation, which says that which says delta x is equal to v sub x times t, which is the same as v0 sub x, and v sub x is equal to v times, well, the x component is the adjacent side to the angle, so it's going to be the cosine of 24 degrees, and we said v was equal to 20, so we have 20 meters per second times the cosine of 24 degrees. So 20 times the cosine of 24 degrees is 18.3 meters per second. So our delta x is equal to v sub x, which is 18.3 meters per second, times the time, which we just figured out is 1.78 seconds. Meters per second times seconds is meters. So we multiply 18.3 times 1.78, and we get 32.5 meters. So it's 32.5 meters from the edge of the cliff. So let me just double check. Okay, so I've checked it, and that all works out. So let's kind of review what we did here. We had two parts of the problem. We had the car accelerating down the ramp at an acceleration of 4 meters per second. Started off at rest. We had the total distance along the ramp at 50 meters. So we just used one-dimensional stuff for the first part. And using the one-dimensional equations, this one in particular, knowing v0 is 0, acceleration is 4, and delta s is 50 meters, we could solve for the final velocity. So that's the final velocity coming right off the ramp. Well, when it leaves the ramp, it's moving at the same angle. So the second part of the problem says that the car started at an angle of 24 degrees with a speed of 20 meters per second. And so we could find the x and y components of the velocity. We used the y direction to find the time. First we calculated the velocity, then the time, just because we didn't have to deal with the quadratic equation. So we started here at a distance of 30 meters, and we went to a distance of 0 meters for a delta y of negative 30. We calculated the initial velocity in the y direction by just using the trigonometry of this vector, and we found that the y component velocity was negative 8.13. delta y is negative 30 meters. So we use this equation because you can solve for velocity. V0y is negative 8.13, delta y is negative 30. That works out because these two multiplied together gives a positive number, which means the velocity is increasing, and it does increase. It increases from 8.13 meters per second to 25.6 meters per second. So that's expected. As something falls, it should go faster. So knowing the y component of velocity, we can then use another one of the four equations. This one, solve for t, plug in the final velocity, the initial velocity, and the acceleration due to gravity. We find out it's 1.78 seconds. So with that time of 1.87 seconds, we can then go over to the other equation. This is our linkages of time, and we can use just constant velocity results. There's only one equation that says delta x is equal to the x component of velocity times time. The x component of velocity is equal to the original velocity times the cosine of 24 degrees, because the horizontal is the adjacent side. So we use the property associated with the adjacent side, which is the cosine. So we take 20 meters per second times the cosine of 24 degrees, gives us this part, 18.3 meters per second. So that's our x component. We multiply that by the time, gives us the x change in displacement of 32.5 meters. Okay, so we're going to do problem number 54. So let me write that down, problem 54. And it's Daredevil. He's going to jump over this canyon. So let's make a canyon made out of squares. So there's the two sides of the canyon. Its walls are equally high and 10 meters apart. So the equally high just means that the initial height is the same as the final height. Let's see if I can make that happen. The distance here is 10 meters. So here, let's define this as the initial point right here. So let me. So this is x and y equal to 0. So x, y. This is a 0 point. So what we can say is that x, which is the final displacement in the x direction, is equal to 0, the initial displacement, plus 10 meters. So it's going to be 10 meters. The final height is going to be equal to the initial height, which is 0 meters. So y is 0, so or delta y. You could also say that delta y is equal to 0 meters. There's not going to be a change in height. So theoretically, this guy, you have to have some kind of ramp that would cause this thing to go up like this. So he comes up, gets to maximum, and then comes back down, and lands at the same height. Okay, so he takes off by driving a motorcycle up a short ramp sloped at an angle of 15 degrees. So we're going to make a little bit larger shape, a little. So actually, it's going to look more like this, really. So this is 15 degrees, and then he's going to come down. The height of the top of the ramp is also the height of the other ramp. If you just went to flat, you go, but here, if he comes up at this angle, he's going to come back down the same angle. So he'll be much happier about that. If you ever watch motorcycles jumping, you know what I'm talking about. Okay, so that's 15 degrees. This is what minimum speed must he have in order to clear the canyon. So we have two relationships. We have the x direction. So the x direction here. And the x direction says that v sub x is equal to v0 sub x, and also that delta x is equal to v sub x times time. And the y direction, we have that v and v0 sub x is equal to v times the, well, the x direction is the adjacent side in this right triangle, so it's going to be the cosine of 15 degrees. Now, in the y direction, we have that v0y is equal to v times the sine of 15 degrees. And we also know that delta y is equal to v0y(t) plus 1/2 a t squared. And our acceleration is negative 9.8 meters per second squared. We also know that delta y is equal to 0. So let's think about this. How many unknowns do we have and how many equations? We have two equations, this one and that one. So our knowns are, we know that delta x is equal to 10 meters. We know the cosine of the angle. What else do we know? We know the acceleration is negative 9.8 meters per second squared. Our unknowns are v, the speed, and t, the time. Now you say, well, I don't know v0y, but I do know v0y because I know v. So we should be able to manipulate these two equations and come up with one equation in terms of, in this case, speed. So let's go ahead and do that. So delta x is 10. V sub x is v times the cosine of 15 degrees, and then we multiply by time. So we can solve for time in this equation. T is equal to 10 divided by v times the cosine of 15 degrees. Second equation, this is this one. Delta y is 0. Delta y is 0. v0y is v times the sine of 15 degrees. So that's v0y times time plus 1/2 a, I'm going to leave this as a right now until we solve everything, times t squared. So I can then substitute in for t here. So we're using substitution. 0 is equal to v times the sine of 15 degrees times t, which is 10 divided by v times the cosine of 15 degrees. So that's that part, plus 1/2 a times t squared, which is t is 10 divided by v times the cosine of 15 degrees. Well, this v cancels out with that v, and this is squared. I'm going to make sure I square that. So let's see what we can do here. So I only have one unknown, which is v. So let's sine of 15 divided by the cosine of 15 is tangent of 15. And if we subtract that from both sides, we'll have negative 10 times the tangent of 15 degrees. On the right-hand side, we have 1/2 a, and we have 10 squared, which is 100, divided by v squared times the cosine of 15 degrees squared. So now we just need to solve for v. So you can kind of set up ratios here to put this over 1. And so these are in the numerator, that's in the denominator. So what we could say is v squared is equal to, okay, so we have 100 times a from here. In the denominator we have 2. We have the cosine of 15 degrees squared from here. And we divide by 10 times the tangent of 15 degrees. And we have a negative sign too from there. Tangent of 15 degrees. And since the acceleration is negative, everything's going to work out. So let's now plug in the accelerations. They have negative 100 times. And there's other ways that you can manipulate these if you wanted to. That's what I'm doing. meters per second squared divided by 2 times 10 is 20 cosine of 15 degrees squared times the tangent of 15 degrees. Let's just plug that into the calculator. Hopefully we get the right answer. Didn't make a mistake. Easy to make mistakes. Times 9.100 times 9.8. 9.8 divided by 20 divided by the cosine of 15 degrees squared. So let's do that. Cosine 15 squared divided by the tangent of 15. And I get 196 meters squared per second squared. So when I take the square root, I get 14 meters per second. Okay, so let me just check the answer and see if I made a mistake. So I'm happy because that's the right answer. Now it will be plus or minus 14, but of course it has to be positive because we're moving from left to right. So, and 14 meters per second is, we can convert that. Let's convert that to miles per hour. They didn't ask us to do it, but let's see. We have 14 meters per second is meters per second is 2.237 miles per hour. So I just need to multiply that by 2.237. So 14 times 2.237 is 31 miles an hour. So it doesn't have to be moving. So it's not a real big jump. So that's equal to 31.3 miles per hour. So it's not like an Evel Knievel jump where he's trying to jump across the Grand Canyon.
Okay, so this is problem number 5 for chapter 3, which is 311 in the university physics book. So what we have is we have 2 crickets, and they're standing on a cliff. So here they are. And one is just steps out and goes, falls down. The other one jumps out horizontally. And let's see, who is who? So Chirpy drops. Chirpy is here. And the other one is Mulata. I don't know if it's a Spanish cricket. And the question is, if it takes the time for Chirpy to drop 2.7 seconds, how far from the edge of the cliff is Mulata? So the whole idea here is that whether you step out and just fall, or whether you jump horizontally, it's going to take the same amount of time, because the laws in the vertical direction still apply for both cases. So let's define x and y equals 0 down here. So our initial height is going to be something. We don't know what that is. And let's define y up as being positive, and to the right, x being positive. So what we can do is we can find the time it takes for Chirpy to drop, and then use that time to figure out how far Mulata goes horizontally. So the first thing is the Chirpy part. And again, we need 3 things associated with the y direction. Actually, we already know what the time is. We need to know what this distance is. Well, if they already gave us the time, then we don't even actually need to know how high the cliff is, I don't think. as I just said, once we know the time, we can apply that. Man, this seems too easy. But it doesn't ask us for how far above the cliff Chirpy is. We could calculate that, but we don't need to know it for the problem. Let's go ahead and calculate it anyway. So if we do the Chirpy thing here, what we have is that V0y, the initial y velocity for Chirpy, is 0 meters per second. We need the acceleration in the y direction is negative 9.81 meters per second squared, because up positive y is up is positive y, so we have the acceleration negative, and we have time equals 2.70 seconds. So we have three things in the y direction, and we use the four equations that apply to constant acceleration. This is a constant acceleration of negative 9.81 meters per second squared. So if we want to calculate delta y, we could use delta y is equal to v0 yt plus 1/2 a sub y t squared. In this case, v0 y is 0, so it just simplifies down to delta y is 1/2 a sub y t squared. So we get a sub y is negative 9.81 meters per second squared, and t is 2.7 seconds. So we get 2.70 seconds squared, and we've got three significant figures in this problem. And we're going to get a delta y of negative, because we're going down, we're falling down. Okay, so we get 0.5 times negative 9.81 times 2.70 squared, which is 35.8. Negative 35.8 meters. So it's a fairly large cliff this guy's jumping off of. But as I said, we don't actually need this. That's not being asked in the problem. All we have to do really is use the x direction equations for Malada. And x direction is constant velocity. And we only have one equation for constant velocity, which says delta x is equal to v0x times t. And we have to convert centimeters per second to meters per second. So that's 35.95 centimeters per second. And we have to divide that by 100 centimeters per meter. So we'll get 0.95. That's 95 divided by 100. And the units are centimeters per second, and then take the reciprocal. So you get meters per centimeter if you take the reciprocal of the units. So the centimeters cancel out, and we get 0.95 meters per second. So that's the x component of the initial velocity for Malada. And so the distance is just going to be 0.95 meters per second, the initial velocity, which stays constant, and the time, which is 2.70 seconds. I should carry an extra digit here. Did they say 95.0? Yep, so this is 95.0, so there's three significant figures. The conversion has an infinite number of significant figures. 0.95 times 2.7 is 2.57 meters. Or if we wanted to convert that back to centimeters, we'd multiply by 100, so that would be 257 centimeters. Okay, let me just check the answer. Okay, so that's it. Okay, so this is problem 6, which is for chapter 3, which is problem 312 in the university physics book. So this is a football quarterback, and so here he is, and he's going to throw a ball, and the ball is going to have both an x and y component. So they give us the two components. It says the upward velocity component, which is the vertical component, is 12.0 meters per second. That's v0y. And the horizontal component is 20.0 meters per second, and that is v0x. And we'll define the coordinate system here so that positive x goes from left to right, positive y goes up. So in the y direction, we have that the acceleration in the y direction is negative 9.81 meters per second squared. v0y is positive 12 because it's upward meters per second. And the first part of the question asks us how much time is required for the football to reach the highest point of the trajectory. So at the highest point, I'll call it Vy1. This is just meaning the first part of the problem is 0. So anytime you get to the peak of your trajectory, your y component is 0. Now in the x direction, all we only need the velocity, because the acceleration in the x direction is 0 because it's constant velocity, and v0x is given as 20 meters per second. So we're going to do the y direction, and what we need to do is the first thing they're asking for is that our two unknowns are delta x or delta y and t. So they're asking us to solve for t, and the question is which equation do we want to use? So if we say delta y is equal to v0yt plus 1/2 a sub yt squared, here we don't know two things, so that's not going to work out, is it? So that seemed like a good idea, but it probably is this second equation. V sub y is equal to v0y plus a sub yt. So let's check it off what we know. We know Vy is 0. We know V0y. We're given that. We're given the acceleration. So that's the equation we use. And if we solve for t algebraically, we'll get V sub y. I'll put a subscript of 1 here. V sub y1 minus V0y, or V sub y0. I guess I should be consistent here. Divided by a sub y. Okay, so t1, time to get to the peak, which is going to be, draw this thing like that. So here's the peak. So this is 0, this is 1. We'll make, when it comes back to the same height, we'll call 2. So v sub y1 is 0. V sub y0, or v0y, is positive 12 meters per second. And we divide by negative 9.81 meters per second squared. So we're in meters per second, so we know the answer is going to turn out with the correct units. You see we got two negatives. We got negative 12 and negative 9.81. So that's going to cancel out. Give us a positive time, which is what we always need. So we get 1.22 seconds. So that's the answer for the first part. It takes 1.22 seconds. How high is that point? Okay, now we can use this equation. We can actually use a lot of different equations. Let's just use this one. So delta y is equal to v0y, which is 12 meters per second, times t, which is 1.22 seconds, plus a, 1/2, times a, which is negative 9.81 meters per second squared, times t squared, 1.22. So we get 12 times 1.22 plus 0.5 times negative 9.81 times 1.22 squared. So we get delta y is 7.34 meters. So that's the second part. Now, just to show that you get the same answer no matter which equation you use, we could use this one, which says v sub y 1 squared is equal to v sub y 0 squared plus 2 a sub y times delta y. Well, this is 0, the y component. So if you solve for delta y, you get negative v0y squared. So that goes to the other side, becomes a negative. And then you divide by 2 and a sub y. So we get negative v sub 0y, or v sub y 0. See, I switched those accidentally. Is 12 meters per second squared divided by 2 times negative 9.81 meters per second squared. And notice this negative will cancel out with that negative, so we'll get a positive delta y, which is what we're looking for. And if you square 12, divide by 2, divide by 9.81, you get 7.34 meters delta y. We could also use the first equation, doesn't matter. Okay, so that's delta y. Question number 3, how much time after it is thrown is required for the football to return to its original level? How does this compare with the time calculated in part A? So, say time 2. So we'll call it, T2 is going to be question mark. We don't know what that is. But we do know that delta y 2 is 0 because it goes up to a peak and then it comes back down. So the actual total vertical displacement is 0. We know that a sub y is negative 9.81 meters per second squared, and we know that v sub y 0 is 12 meters per second. So we know 3 things, and if we think about which equation to use, which one involves t, v0y, a, and delta y? Well, this one, delta y is equal to v y0 by v0y plus 1/2 a sub y t squared, t2 squared, delta y2, that's equal to 0. So we get the same stuff right there. And what we need to do is solve for t. Well, you can see I can cancel one of those out. And so what I'm left with is 0 is equal to v sub y0 plus 1/2 a sub y t. 2. And so T2 is equal to negative V sub y 0. So I'll move this to the other side. It becomes negative. Multiply by 2 and divide by A sub y. Now, how does that compare with the equation that I used for the first part of the problem? Well, I ended up with this went to 0, so I just had v sub y 0 over a sub y, or negative v sub y 0 over a sub y. So what do I have here? I have negative 2 v 0 y over a sub y. So it's going to be twice as much. So we get T2 is equal to negative 2 v 0 y, which is plus 12 meters per second, divided by negative 9.81 meters per second squared. So the negatives cancel out. I get a positive t. So I get 2 times 12 divided by 9.81, which is 2.45 seconds, versus t1, which was 1.22. So T1 is equal to 1/2 T2, or T2 is equal to 2 times T1. So, then that makes sense. It takes as much time to go up to the peak as it does to come from the peak back to the same height. So we probably could have guessed that just by using some reasoning. Okay, so that's the second part. Problem part D says, how far does it travel? Well, the total traveling, so delta, let's say delta x2, how far does it travel in the x direction to T2 is just v0xt. So in the x direction you have a constant velocity. So we say delta x2 is v0x, which is positive 20 meters per second times the time, which is 2.45 seconds. 20 times 2.45 is 49.0 meters, which is about 50 yards. That's a pretty good pass. So that is part D. Part C was this, and this part. And the last part is these curves. So let's plot all of these. So let me just what am I doing? X versus T, Y versus T. Okay. So those are going to be both positive. And then we're going to have, for the velocity, we're going to have to make it so we have both positive and negative velocities. Actually, just for the Y component. Okay. So this is x. It's a function of time. So because the equation here, this x direction equation is just a linear equation, we start off and it's just a straight line like that. So this is x equals 0. If we go over here, this is 49 meters. Well, this is 49 meters. This is 2.45 seconds. Okay, now as far as the y, you start at 0 again because I defined where he threw it from is 0. And it's going to be a parabola. Go like that. It's going to come all the way back down to 0 here, 2.45. This half, the maximum height, we calculated that. Delta y was equal to 7.34. So 7.34 meters. Starts at 0, comes back to 0. The x component of velocity here is just constant, just a horizontal line, it's positive, and the value is 12 or 20 meters per second, constant. Whereas v sub y, it starts out as positive, it's going up, and then it ends up being negative. So the initial velocity is 12 meters per second, and the final velocity is negative 12 meters per second. And the peak occurs where the velocity is 0, where it crosses the x-axis. Okay, this is problem 7, which is 321 in the university physics book. So we have a man who's thrown a rock. We'll assume that we'll define where he throws it from as the zeros here. So this is this is x. This is y, and this is 0, 0. So the ball is thrown at an angle of 33 degrees, and it goes through the peak, and then it comes back down and hits the ground somewhere with some velocity that we're going to calculate. So we're going to have some initial velocity. Here's v0, which is given as 30 meters per second. It has a horizontal component and a vertical component. And so this would be v0x, and this would be v0y. Let's call this point 1 and this point 2. So the first part of the problem, we have an initial velocity. We have v0x and we have v0y. And we can calculate those by taking v0 and multiplying by, well, let's put theta in here. Theta is 33 degrees. So v0x is v0 times the cosine of theta, and v0y is v0 times the sine of theta. So we can get the initial x and y components of velocity. We have that ax is 0, because it's constant velocity, and a sub y is negative 9.81 meters per second squared. And that's because I defined y positive going up. So we have velocity, initial velocities and accelerations for the point 1. So we need one more thing, and for the y direction we know that v sub 1y, so it's the y velocity at point 1 is 0.00 meters per second, because it's the peak. Now they're only asking us for the maximum height above the roof, which I'm just finding the roof where he throws the ball. So all I have to do is figure out delta y in that case. So I want to find delta y sub 1. This question mark. But I have three things here. I have v0y. I can calculate that. I know the acceleration in the y direction. I know the final velocity in the y direction. So which equation would he use? Well, what equation has delta y, acceleration, and the velocities, because we don't know what the time is in this case. So it's equation 4, which would say v sub 1 y squared is equal to v sub 0 y squared plus 2a sub y delta y sub 1. But in our case, v sub 1y is 0. So this is all equal to 0. If I solve for delta y, what I'm going to get is this is going to go to the other side, so it'll become negative. So you get negative v0y squared, and then you have to divide by 2 and divide by a sub y. So that's the equation. Delta y1. So delta y1, plug in our numbers, v0y, well, we got to calculate that, so I haven't done that yet. So let's v sub 0 is given 30 meters per second. And we multiply this by the sine of 33 degrees. Let me just move these down a little bit. So make sure your calculator is in degrees. Okay, mine's in degrees. I don't know about yours, but so we got 30 times the sine of 33. So I get 16.3 meters per second. Units for the sine are, there are no units for trig functions. So we still continue with the same units. And that kind of makes sense. Sine of 30 degrees is, sine of 30 is a half, which half of that would give you 15. So it's a little more than a half. Okay. So now we can plug it in here. So it's going to be 16.3 meters per second squared divided by 2 times the negative 9.81 meters per second squared. Notice the negatives cancel out, and I get a positive delta y, which I would expect from my definition of y positive going up. So we get 16.3 squared divided by 2 divided by 9.81. So I get 13.5 meters. So that's the answer for part A. So if I look at, the distance here I'm talking about is the distance above the roof, because I defined the roof as 0. So what did I say it was? 16.3. Now, the second parts of the problem, part 2 here, is we're going all the way to ground. So delta y2 is negative whatever the height of the building is, 15 meters. Our acceleration in the y direction is negative 9.81 meters per second squared. And we're starting all the way back to the beginning. And again, you don't have to start at the peak. You can just start at the beginning. You could start at the peak. Then your delta y would be 15 plus 13.5 would be negative 28.5. But I'm just going to start at the beginning again. And so I have the same v0y. v0y is, what did I say it was? 16.3 meters per second. So these are the three things I know. And what are they asking for? They're asking for the speed of the rock just before it strikes the ground. So we need to calculate the velocity. We're looking for v sub 2y. And we know all that. Well, that's equation 4. We know the v2y squared is equal to v0y squared plus 2a sub y delta y sub 2. And this is already solved for the thing we're trying to figure out. Like I said, I usually solve for v sub y squared and then take the square root. Now, this is not the final velocity. This is the final y component of velocity. So I need the final x component of velocity, but the final x component of velocity is the original x component. So let's go ahead and calculate that while we're at it. 30 meters per second times the cosine of 33 degrees. So 30 times cosine of 33 is 25.2 meters per second. So that's v0x, which we'll need later. Okay, so let's do this right here. Okay, so we got 16.2 meters per second squared plus 2 times a sub y, which is negative 9.81 meters per second squared, times delta y, which is negative 15 meters. So 16.3 squared plus 2 times, so you see I've got two negatives, so I'm just going to multiply the positive numbers together. So I get v2y squared is equal to 560 meters squared per second squared. And then I take the square root, so v2y is equal to plus or minus the square root of 560 meters squared per second squared. Let's take the square root of that, 23.7 plus or minus meters per second. So I take the square root of the number and I take the square root of the units. So this is my y component. Now the thing here is that it's negative because the final velocity is going down. Now you might say, where's the positive solution? Well, the positive solution would be if you threw the ball from here to the ground at some velocity, so that when it reached this point in space, that it would have the initial conditions. So it's kind of it's not a real solution. So we just have to look at the problem statement. So we're going to put plus and minus there, but then the next step is we say it's negative 23.7 meters per second. So our total velocity, v2, is equal to the square root of v2x squared plus v2y squared. So what's happening here is you have this x component, v2x, which is the same as the original x component, 25.2, because it doesn't change. So this is 25.2 meters per second, and then you have this downward component. So this is v sub 2y, which is negative 23.7 meters per second. And then you draw your resultant vector, which is here. So this is v2. And you see I create this right triangle. If I shift this down, I have this right triangle. So this is the hypotenuse of a right triangle. This is 90 degrees because the x and y are 90 degrees relative to each other. So we take the square root of v sub 2x, which is 25.2 meters per second, quantity squared, plus v sub 2y, which is negative 23.7 meters per second squared. And you see, because I square them, they both become positive. So you get 25.2 squared plus 23.7 squared. And then you take the square root of that, and you get v2 is 34.6 meters per second. So that's the final velocity. So that's the answer for the speed. Now the horizontal range, you use delta x2 is equal to v0x times t2. So we need to time t2, and the way you would do that is you would use any one of the equations, which we said you can use the second equation is always the easiest one to use. So there's v2y is equal to v0y plus a sub y times t2. In this case, these are both non-zero. So first thing we do is we subtract v0y from both sides, and then we divide by a sub y. So you'll get t2 is v2y minus v0y divided by a sub y. So t2 is v2y, which we got over here, was negative 23.7 meters per second. Subtract v0y, which was v0y is 16.3 positive. And then you divide the whole thing by negative 9.81 meters per second squared. And you can see, I get a negative number in the numerator divided by a negative number in the denominator. So I get a positive time, which makes me very happy. So if I carry out that calculation, I get T2 is 4.08 seconds. And then I can use that time up here to calculate delta x. So I have V0x, which was 25.2 meters per second. I multiply by T2, which is 4.08 seconds. So delta x is 103 meters. Again, I'm rounding out to 3 significant figures. So that's the horizontal range of the rock just before it strikes the ground. And then finally we have our graphs of delta y, delta x. So this is going to be delta x. We'll do the two displacement things. I'm going to draw my one for delta y here. So this is delta x. So that's just a linear relationship, just a straight line. So here at the final time, which was 4.08 seconds, if we go up here to this point and go over there, that is 103 meters. As far as delta y is concerned, we start at 0. So this is delta y. So we go through some place where it's a peak, and it's a parabola because it's constant acceleration, and then it comes down like that. So this height, the maximum height, which we calculated earlier, which was 13.5 meters. Then we come back down through the original height, and then we keep going. And this distance here at the end of the flight is negative 15, right? Negative 15 meters. So the distance from the top of the building to the bottom of the building is 15 meters. Now the velocity, the x velocity is constant, positive, it's just a horizontal line. The y velocity is going to be so what we do is we start at a positive. So the velocity curve is a straight line. So we start at positive, then we go through 0 at the peak, and then we become more negative. So here it's a horizontal line. This is v sub x. So the x component velocity was x component was 25.2. Now here this one was 16 point something, 16.3. And the final y velocity was negative 24 basically. So that's going to be down here somewhere. Negative 24. So I probably should spread the shift this out a little bit like that. Okay, so I'm going to pause it, make sure I got everything right here. Hopefully I did. Okay, so it's correct.